The research proposes SECRM-2D, an RLBASED autonomous driving controller that optimizes efficiency and comfort while ensuring safety and following a prescribed route. It extends previous work by incorporating both discretionary and mandatory lane changes. The controller's safety constraints are derived from the Vienna Convention on Road Traffic, ensuring the gap between the vehicle and its leader is positive and sufficient for reaction in case of emergency braking. The objective is to maximize a weighted combination of efficiency and comfort, subject to safety constraints and route following. Efficiency is measured by speed, and comfort by jerk. The controller's performance is evaluated in simulated scenarios, showing it successfully avoids crashes and outperforms baselines in efficiency and comfort. This work advances RL's potential for training performant AV controllers with strong safety guarantees. The SECRM-2D model is a two-dimensional state space representation for a vehicle control system that aims to optimize the efficiency and safety of the vehicle's movement. It considers both longitudinal and lateral movements, making it more comprehensive than its unidimensional predecessor. The model utilizes a statewise constrained Markov decision process, SCMDP, to formalize the control problem as an optimization issue. In the context of the SCMDP, the state space includes various features such as the ego vehicle's distance from the start of the current section, speed, previous acceleration, section index, lane index, lateral speed, and a Boolean map indicating whether a lane is part of the ego vehicle's route. Other vehicles within a fixed scan radius are also considered, with their state representations consisting of longitudinal distance, speed, and acceleration. The action space consists of a two-tuple, alpha, L, where alpha is an acceleration action and L is a lane change action. The acceleration action is continuous and subject to state-wise constraints, while the lane change action is discrete and subject to constraints that prevent unsafe changes. The reward function is a weighted sum of four terms: efficiency, comfort, route following, and safety. The efficiency term penalizes the difference between the current speed and the target speed, which is determined by the safety constraints and the speed limit. Comfort is measured as the square of the jerk of the ego vehicle, with a penalty applied for higher jerk values. Route following is enforced through a cost function that discourages the use of lanes not part of the route. Safety constraints are also enforced through cost functions, ensuring that the vehicle maintains a safe gap and adheres to the speed limit. The objective of the agent is to find a feasible policy that maximizes the cumulative discounted reward, which is defined as the sum of the rewards over an infinite time horizon, discounted by a factor of gamma at each time step. This setup allows the agent to balance between improving efficiency through discretionary lane changes and minimizing the risk of missing its route, depending on the value of gamma. The research focuses on developing a unified framework for autonomous vehicles to optimize both discretionary and mandatory lane changes. The discretionary lane changing reward is designed to encourage the vehicle to switch to a lane with a higher target speed, while the mandatory lane changing term ensures the vehicle follows its intended route. The overall optimization objective is to find the optimal policy that balances these two aspects. The framework uses the Deep Deterministic Policy Gradient Algorithm, DDPG, for training, which is particularly suitable for continuous action spaces. The DDPG algorithm updates both the critic and actor networks, ensuring the policy maximizes the expected cumulative discounted reward. The training setup utilizes the Sumo simulator for realistic traffic scenarios. The framework's hybrid learning approach considers the current traffic environment to calculate the maximal safe target speed, deciding on longitudinal acceleration and lateral decisions. Through feedback from the environment, the RL algorithm learns the optimal policy. The research paper discusses the development of a safety-aware autonomous vehicle control system. It presents a novel framework that enforces safety through action constraints rather than a safety term in the reward function. The system is trained using deep deterministic policy gradients, DDPG, in two environments: a simple loop network and a network based on a real-world freeway. In the loop network, the focus is on efficiency, comfort, and discretionary lane changing, while the QEW network evaluates route-following tasks alongside efficiency and comfort. The uncontrolled vehicles are modeled using the Krauss car-following model and the SL2015, lane change model. The system's training configuration, including parameters like discount factor, simulation time step, and learning rates, is detailed. The convergence of efficiency and comfort rewards during training is shown, indicating the system learns to balance safety and efficiency. The paper concludes by analyzing the long-term longitudinal behavior of a collection of vehicles, demonstrating the formation of platoons at the same speed as the lead vehicle. The summary begins by discussing the stability of the equilibrium point, G** operator, V** operator, for the system, which is proven to be asymptotically stable. The Jacobian matrix analysis shows that the eigenvalues have norm less than 1 when W greater than 0, ensuring stability. The case where W equals 0 is also addressed, with complex eigenvalues indicating instability. The removal of simplifying assumptions is briefly discussed, highlighting the need for an initial speed-up period or a speed limit to ensure the follower can catch up with the leader. The qualitative implications for SECRM-2D platoon formation are then presented, expecting a well-trained model to form a platoon with a common velocity and intervehicle gaps described by the previously obtained formulas. This expectation is confirmed by empirical tests, as seen in Figure 10. The section concludes by noting that if speed limits are applied, it may not be possible for a follower to catch up, leading to the formation of multiple platoons. The research focuses on improving safety in autonomous driving by introducing the safe, efficient and comfortable RLBA-SED driving model with lane changing, SECRM-2D. This model extends previous work by incorporating hard analytic safety constraints on acceleration and lane change actions. The evaluation involves 3 scenarios: bypassing, emergency braking, and merging. In the bypassing scenario, SECRM-2D successfully generalizes to unseen configurations, achieving 0% crash rate and outperforming baselines in efficiency and comfort. Emergency braking results show a 0% crash rate for SECRM-2D, further emphasizing its safety. The merging scenario demonstrates the model's ability to generalize to different route-following scenarios without retraining. The results highlight the advantages of SECRM-2D over existing RLBA-SED controllers, particularly in safety, efficiency, comfort, and route following. The summary begins by discussing the long-term equilibrium of a platoon of SECRM-2D vehicles moving at constant speed, including the precise expression for inter-vehicle gaps in terms of speed and vehicle configuration. It then transitions to a detailed analysis of the stability of the follower with a constant speed leader system, verifying that the eigenvalues of the Jacobian matrix at the equilibrium point satisfy lambda plus or minus less than 1 whenever W greater than 0. The discussion highlights the importance of this stability in ensuring safe and efficient traffic flow. The summary also touches on the research team's expertise in reinforcement learning and intelligent transportation systems, including their work on car-following models and lane-changing strategies. It concludes by emphasizing the significance of their findings in improving urban freeway operations through the integration of artificial intelligence and transportation engineering principles.